Let's take a look at a little more challenging problem here in arc length. This one is this function, which is got a cubic term and then a 1 divided by x or 1 divided by 2x term over the interval from 1/2 to 2. So I've graphed the portion of the function that we need. We're going from x equal 1/2. And if you plug in 1/2 into this function, you're going to get an output of 1, it turns out, all the way up to x equal 2. Right. And so on the length we're looking for is this segment here of the curve. What's the length as we go from one point on the curve to the other? Okay, so let's remind ourselves of the arc length integral. It's going to be the integral from a to b, the square root of 1 plus, we'll just say y prime squared. Right. And of course, our interval is a is 1/2, b is 2, and our function is there. So let's find the derivative. Let me just rewrite this function first of all, 1/6 x cubed. What I would like to do here, some of you might be thinking I have to use a quotient rule here, but I'm going to write this 1 divided by 2x as 1/2 times 1 over x, which is just the same as x to the negative 1 power. So I'm going to avoid using the quotient rule by simply rewriting and now using the power rule. So what is the derivative? Bring the 3 down, 3/6. 3/6 is 1/2. Subtract 1 from the power. Bring the negative 1 down, it's minus 1/2. And subtract 1 from negative 1 gives me negative 2. Okay, so now I need to square this derivative. I want you to recall, be very careful when you're squaring binomials. Many of you have made mistakes, and we want to be very careful about that. In other words, when I'm going to square the difference of two things, some call 1a and 1b. When you square this, you simply can't square a and then square b and take the difference. That's not correct. It's really going to be right. This is really what a minus b times a minus b. So if you do first times first, you get a squared. The outer is negative ab and the inner is negative ab. So that's a total of negative 2ab. Last times last, negative times negative is positive b squared. So that's what you actually get when you square a minus b. And so that's what I'm going to do here. I'm going to square, I'm actually going to do 1 plus y prime squared, right? So 1 plus what? Well, when I square this, this is the a, 1/2 x squared, and the b is 1/2 x to the negative 2. So I'm going to get 1/2 x squared squared, that's the a squared part, minus 2 times a is the 1/2 x squared times b, which is the 1/2 x to the negative 2, and then plus b is 1/2 x to the negative 2 squared. Okay. Now, we could do all the work here, but I'm going to focus in on just, first of all, this right in here. What does this stuff all multiply together to give us? Think about that for a minute. What does that give us if I multiply that together? Well, 2 times 1/2 is 1, times 1/2 is 1/2. And what happens here? X squared times x to the negative 2. Well, remember, x to the negative 2 is 1 divided by x squared. X squared divided by x squared is just 1. Or if you add the exponents, 2 plus a negative 2 is 0, and x to the 0 is 1. So that's 1, and you're just left with 1/2 here. It's negative 1/2. It's negative 1/2. Okay. But I can simplify now because 1 minus 1/2 is just a positive 1/2. But the way I'm going to write this now, I still got this 1/2 x squared squared, which if you square it out, it's 1/4 x to the 4th. Yes, it is. But I'm going to do 1 minus 1/2, and I'm going to put it right here. It's what? Plus 1/2. And then we've got this 1/2 x to the negative 2 squared. Again, that's 1/4 x to the negative 4th power, right? Multiplying the exponents. So you could do that. But just take a minute, because remember, we're trying to simplify this in a way. If I can make this stuff under the radical a perfect square, the square root of a perfect square is, we could simplify. And we can do that because notice here, I have now basically the same thing we had above here, right, which was the a squared minus 2ab plus b squared, except the negative here has become what? Positive. So in other words, this is the same as 2 times 1/2 x squared times 1/2 x to the negative 2, right? It's all 1/2, but it's now positive. So what happens when we change, what happens if I change this to a positive? What if that's now a positive? Well, this will be positive to factor it. In other words, if I multiply out a plus b, if it was a plus b, right, plus plus, then this is going to be plus, right? Because the outer and inner are both positive ab. You still got the a squared, you still got the b squared, right? So in other words, this all factors as a plus b. Okay. Got a dog barking in the background. I hope that doesn't come over the microphone. We'll see. So I've got a plus b quantity squared, right? And so that's what I have. And now I can plug this into the arc length formula, take the square root of that, and I just get, right, what's inside the parentheses here. So here's my arc length. I'll say L for arc length. It is from A to B. A, remember, is 1/2. B is 2. And the square root of this stuff is just this stuff. So it's a little bit, a little bit tricky to get here, right? You got to think about, simplifying, and I kind of gave a hint, in the fact that, using this formula, we can expand this out, but then by combining the 1 and the negative 1/2 here, we're able to then refactor this in a way that allows us to simplify the arc length integral. So now it's pretty routine to do. What's the antiderivative of 1/2 x squared? Well, it's 1/2. Antiderivative of x squared is 1/3 x cubed. And what's the antiderivative of x to the negative 2? We'll add 1. It's x to the negative 1 divided by negative 1. And we're evaluating this all from 1/2 to 2, right, this whole thing. I can simplify in here a little bit. So 1/2 times 1/3 is 1/6 x cubed. And then I've got negative 1/2, and the x comes down below. So it's negative 1 divided by 2x. So let's do that first. And then I can plug in 2 here. 2 cubed is 8. I get 8/6. 8/6 simplifies to 4/3. And when I plug in 2 here, I get 1 divided by 2 times 2 is 1/4. So there's plugging in, plugging in 2. And then plugging in, this is 1/2, remember? Plugging in 1/2. Well, if I take 1/2 and cube it, so I'm subtracting, right? Evaluated 1/2. 1/2 cubed is 1/8. 1/6 times 1/8 is 1/48. And then plugging 1/2 in here, 2 times 1/2 is 1. 1 divided by 1, I just get 1. Okay. Now, again, you can use your calculator to use the convert to fraction key, but it's pretty easy. My least common denominator of all my fractions is 48. 3 goes into 48 16 times. Okay, 16 times 4 is 64. So that's 64 48. That's what 4/3 is. 4 goes into 48 12 times. So I get 1/4 is 12 48 minus the 1/48. And then minus a negative, that's plus 1. And 1 would be what? 48 over 48. So now I have a common denominator. I can add all those up. And when I do, 64 minus 12 minus 1 plus 48 turns out to be 99 over 48. Well, I can simplify further because 99 and 48 are both divisible by 3. 3 goes into 99 33 times. 3 goes into 48 16 times. And there is your arc length, which is going to be just over 2, right? If we want to do 33 divided by 16, well, it's 33 minus 16. 33 divided by 16 is about 2.0. Well, exactly, excuse me, exactly 2.0625. So that is the length. Does that seem reasonable that that length is just over 2? Yeah, it seems reasonable looking at the picture and the dimensions there. Okay, so that was a much harder one. In general, again, remember, if we just give you an arbitrary function here and ask you to find the arc length or the surface area of revolving, which is what we're going to do next, then you're often not going to be able to find the antiderivative. And so a lot of times you can use what? The rules we've recently looked at in terms of approximating integrals with like trapezoid rule, Simpson's rule, and so on. Okay. All right, let's talk about surface area real quick here, introduce you to that and do one example. So the surface area of a solid of revolution. So we looked at solids of revolution before and we were interested in the volume. Now we're going to be interested in the exposed surface of that curve as it goes around. In this case, we're just going to go around the x-axis. Okay. So we're going to rotate it about the x-axis. This is the formula you actually get. Now, why is this the case? Well, first of all, I want you to look in there. If you get rid of that f of x in the integrand, you'll see, hey, that's our arc length, right? That's our good old arc length. Okay, but then we got a 2 pi, and then we got inside the integral, the function itself, f of x. So how is that all going to play out? So if we look at, on the interval from a to b, some curve, and let's just suppose the curve looks something like that on the interval from a to b. Okay, so I'm going to rotate that about the x-axis. Okay, and it's going to come back and go into the page and over down here, right? And as I rotate it, of course, the cross sections we know are circles. Right. But what I'm trying to get at is I want this exposed surface here is what we're looking at, right? And goes around. If I look along the positive x-axis back, I'll see an open hole through this object, right? Circle there. I'm not trying to find the area of that circle. It's just the exposed surface here. Okay, going around. And so first of all, you've got the arc length, right? That's contributing here. What's this 2 pi f of x? Well, if you take at any point x, right, on the interval from a to b, and you do a little slice here, right? What are you going to get? You're going to get a circle, right? A circle. Now, when we were doing the volume, we want to know the area of the circle, right? But now we want the distance around, so to speak, right? And what is the height of this, or what's the, not the height, but what's the radius of this circle? Well, it's the height of the curve. Yeah. The radius of this circle is just the function f of x, right? It's just the function f of x. And what is the distance around any circle? It's the circumference, which is pi times the diameter, or 2 pi times the radius, and the radius is f of x. So the distance around would be 2 pi times f of x. So it kind of makes sense where that 2 pi f of x is going to come in times the length of the arc, right? This arc length, right? Kind of makes sense. So this is not a rigorous definition of proof of how this formula came about. We could do that, but I want to focus on just applying this formula. Okay, but it kind of makes sense if we think about rotating this curve about the x-axis, that the surface area, right, of that solid that we form is given by this integral. Okay, so let's see. It's basically the same when we're evaluating as the arc length integrals, except we've got this, of course, 2 pi out here, and we've got our function here. So let's take a look at this example. Find the surface area of the solid of revolution formed by revolving y equal x cubed. Here's y equal x cubed from x equals 0 to x equal 1. So if I look at this, then rotating this curve about the x-axis here, it's gonna go in, right? Look exactly like a mirror image down here, and we're gonna have circles, right, coming in. So it's kind of like kind of like I don't know, strange flaring out, horn. Maybe if you want to blow in this end, you'll blow out a big, something like a big horn. But again, what we're wanting is this surface here, right? So what's this surface as we go around right there? Okay, not this big circle. What's the surface area? So sort of like if I put it this way and I've got a little sharp tack, right? Don't sit on that. That's going to hurt. But what's the surface area? What would I need? How much paint would I need to paint this portion? Okay, that's the surface area. So our function is, we'll just do f of x, is the function y is x cubed. And so I need to find the derivative, which is a piece of cake, right? 3x squared. And then the derivative squared is 9x to the fourth. And so our surface area is 2 pi. We're going to go from 0 to 1. And it's the function, so that's x cubed, times the square root of 1 plus f prime of x squared is 9x to the fourth. Sorry, I'm off the screen. Okay, so now it's just a matter of evaluating this, and we're going to use substitution, and it's going to work. You'll see if I let u be the stuff under the radical, then what is my du? Derivative of this is 0, and bring the 4 down, I get 36x cubed dx. Of course, I've got an x cubed dx there, so I just multiply both sides by 136 to balance it out. Okay. Only other thing we need to do is change our limits of integration. X is 0 is where we start. In that case, u is what? 1 plus 9 times 0 is going to be 1. And when x is 1, I get 1 plus 9 times 1 to the fourth is 1, I get 10. And so my surface area is now what? 2 pi. And this 1/36, well, we'll just do it this way. X is 0 is now u is 1. X is 1 is now u is 10. And then the x, well, I got the square root of u, or u to the 1/2. And then I've got the x cubed dx left, right? X cubed dx, which is what? 136 du. So I can pull that 136 out, and the 236 becomes what? 2 divided by 36 simplifies down to just 1/18. So I have 1/18 times pi, or I'll just write pi 18ths, right? Pull that 136 out. And then I'm left with u to the 1/2 du. Well, find the antiderivative now. What's the antiderivative of u to the 1/2? It's going to be 2/3 u to the 3/2. Right? And we evaluate it at the upper limit of 10 and the lower limit of 1. I do get a little simplifying. 2/3 times pi over 18. 2 goes into 18 9 times, so I get pi divided by 27. And then u to the 3/2, so 10 to the 3/2 minus 1 to the 3/2. And of course, 1 to any power is 1. So there's the exact value. We can use our technology to evaluate that real quick. So I've got pi, put that in parentheses, pi divided by 27 times, and then in parentheses 10 to the, in parentheses 3/2 power minus 1. Because again, 10 to the 3/2 power, I have no idea how to simplify that. I don't know what the square root of 10 is. I guess you could write as the square root of 10 cubed, the square root of 1,000 minus 1. But it's approximately 3.563. Okay. So again, this gives us the area. So these would be whatever our units are. And we weren't given any units, but they would be square units, right? So like if this was dimensions in feet, we would need a little more than 3.5 square feet, right? In order, of surface area. Like if we're going to paint again that tack, this portion here, we would need enough to cover 3.5 square feet, for instance. Okay. All right, so in the next, we're going to stop the video here. In the next video, I'm going to use the surface area formula here, and we're going to rotate a region that will form a solid that is a sphere, and we will find the surface area of a sphere. And so we'll derive that and prove that to you on the next video.